A2 is inverse variation. A1 was direct variation. Okay, so what do you think that we'll have going on with these kinds of problems? If it's inverse, what does inverse mean?
It's like one value goes up to the other.
Yeah, okay. So instead of as one value increases, the other value increases, now we have as one goes up, the other goes down. Look at our formula. All right. Our formula, instead of being y equals kx, we have y equals k over x. So right away, the first thing you want to point out is that when you see your variables are on opposite sides of the equation, and one of them is in a denominator, it means that they're inversely related. Doesn't matter what the variables are. And you're going to see later today, we'll talk about things like the force of gravity on Earth, and that's over r squared. So that's inversely related to the r that is distance. It's a distance squared. Or it could be, if you solve d equals rt, solve that for r. What do you get? D equals rt. Solve that for r, you get r equals d over t. D over t. So the rate and the time are inversely related. As the time it takes you to complete a task goes down, aren't you working at a higher rate? Right? If I can do the same job you can in half the time, I'm working twice as fast. So they're inversely related. So we're going to see that with our variables. They're going to appear like this always. Okay, so think of, when you learn d equals rt, you also just learn it like this, right? Who saw it this way, that's boxed in when they were younger, or did you see it as d equals rt? Okay. In a lot of the physics students see it this way. So when we look at this xy equals k is rt equals d, and we're just solving it this way. Why is it important that xy equals k? What's the idea there? So, but what do you notice? If x increases in a product, what has to happen to the other number for this to be held constant? Yeah, it needs to decrease, right? If I had something like this, if I had 5 times 3 equals 15, but now suddenly I had some number times 1.5 equals 15. This value decreased. What happens here? What does this number become? 10. It increases. So we're seeing this inverse relationship, and the product is always, not 1.5, but 15, always held constant. Okay, always held constant. This 15 is the same for both of these. So when you look at the graph, what you're seeing is that the height of this graph and the width is opposite of the width of this one and the height. So this is going to be related to calculus when you get, to your later classes in pre-calc. This inverse relationship. This curve here is one of your basic curves in calc that you're going to learn. And traditionally it's written as this. All right, 1 over x. Where 1 could be any number, right? 1 could be 2, 3, 4, some k or constant value. So we call this again the constant of variation. The same term as from last class. All right. So the first one. Read what we have and tell me how you would write what we have. So read it to yourself first and tell me what you would write as a result. Tori May.
You would write 2 over 3.6.
2 over 3.6
equals x over 4.5.
Well, be careful because they're not directly related now. You're setting up a proportion, right? But these are inversely related. So we can't set up a proportion here unless we flip one of our proportions. But in a moment we're going to see something's going to be inversely related to the square. Then it gets confusing to use proportions. So let's stick to the formula we saw on the previous page. Arthur, what do you got?
4.5 equals...
How about this? Let me make a better statement. Using this alone, give me a statement. No numbers. Using this alone. You wanna? Worth? Good. I was saying, do you want to follow up your answer?
D equals K over C.
Sure. That works. I would have written it as the other way around.
C equals...
It doesn't matter, it's the same thing,
Okay.
okay, and we'll see why in a moment. I would have written it this way, because I read C first, and then I read is, C, and then is the equal sign, inversely proportional, K over, D goes there. Okay, so I would have written it this way, but it doesn't matter. Because if I multiply by C, it brings this up. And if I divide by D, it brings this down, doesn't it? So you get to this anyway. So these are the same thing. So we're good. But I would stick with this method just because of the way it's written. But again, it doesn't matter. Now we're told that C is 2 when D is 3.6. So what can I do with this piece of information? Forget the other part, just go to this now. What can I do with that piece of information? Exactly right. All right? So let's multiply both sides by 3.6 to get rid of it. It's currently being divided. Those cancel. We get K equals 7.2. Am I done? I haven't even gotten to part A or B, so I'm clearly not done. But now I have a specific value, so I can write a specific equation. So I'm going to take this equation and rewrite it. I'm going to put a 7.2 in for K. And that tells us the constant of variation is 7.2. Now, what could we have done? We could have just multiplied these two numbers to start. Because remember the fact that the constant of variation is always equal to the product when they're inversely related. We wrote this on the last slide also. We could have started by writing this and just multiplied it to get 7.2. But I prefer to write it this way because I can see it here. I didn't mean to be a pun, that'd be a pun at all. But I can see the relationship. C is inversely proportional to D. All right? Now, using this specific equation, plug in this known to get the unknown. Then plug in this known to get the unknown. Go ahead and work on that on yourself, with yourself, by yourself. Plug in the 4.5 for D. God bless you. What do you get as a result? If you get part A, go right on to part B. Correct. You don't have to put that over 1, right? I know it's reduced, but just write it as the decimal, so you can get rid of the fraction line in the 1. But it's correct. Good. Part A should be very easy. Part B, you have to just, do a little manipulation. Some algebra. Part A is right. Part A. A is right. Solve for D. What is D? Flip these. Look for 6.4 and D. Switch them. Remember earlier? Take a look right here. We switch these two. Just remember, you can always switch diagonally. It's no use in having to multiply and then divide when you know you're going to switch them anyway. Understand it for sure, but just divide these two obviously.
Sorry.
So you're obviously going to get a decimal answer for these, okay? Good. Good. Where's your part A? Right, so it says when D is 4.5, find C. So scroll down a little bit. K should be 7.2. Here. This is what we had, right? Plugged in our numbers. We have our general relationship here because of this part.
Right.
2 and 3.6 were given in these locations. You have your locations next up. units.
Oh,
It should be 3.6 on the bottom and then
And
K
two.
on top.
okay.
Good, and the bottom's 3.6. Now if you solve for K, you get 7.2, right?
Yeah,
All right, now you got that. And you're told that D is 4.5, plug in for D.
okay.
Are we all good on these? We got 1.6 and 1.125. 1.6. Oh, yeah, the second problem was 6.4. So for the second part, what did you have to do? Who can just quickly explain? Part
Part B.
Yeah, why was part B a little more tricky than part A? What did you have to do in part B? There's an extra step.
You had to divide by, or multiply by D and then divide by C.
Yeah, you have to flip these, right? So in this part, you're finding D when you're given C was 6.4.
Oh, I see.
So when you plug in the 6.4 here on the bottom left, okay, right down here, if 6.4 plugged in there, you have to switch these two to solve for D. All right, a word problem. Can I get someone to read it for us nice and loud? Nice and loud. Georgia, go ahead.
For cones of equal volume, the height is inversely proportional to the square of the radius of the base. If the radius of a cone is 10 centimeters and its height is 15 centimeters, find the radius of a second cone of equal volume with a height of 60 centimeters.
So we're told that the height is inversely proportional to the square of the radius of the base. So this is the base radius r squared. It's inversely proportional, so it's in the denominator. The height is here. What goes there? Same as last problem. What goes there? K, the constant of variation, or K. So again, this statement on the board tells me, and this is how I read it, ready? The height is inversely proportional, meaning K over, the square of the radius of the base. The square of the radius of the base. Now, we're given a scenario. We're told that the radius of the cone is 10 and the height is 15. So let's plug them in, right? And what are we going to solve for? We'll solve for K again. We're always going to start by finding K so we know what our proportion is going to look like. Or inverse proportion. So solve for K, let's write our specific equation. So I just changed colors, and you could do that kind of stuff in your notes, please, to help yourself, because some of you guys write notes and then afterward aren't always sure what they mean. Now we're trying to figure out the radius, right? If we go back up to the word part, right here. Okay, so find the radius of a second cone of equal volume with a height of 60. So we know the height is 60 now. We want the radius. Let's solve for the radius generically. How do I get r by itself? This is tricky, so step me through the process.
You would switch H and R squared,
Thank you.
and then take the square root of
Good.
the square root of the front.
And it's really plus or minus, but are we going to have a negative radius? No, we're not. So we don't have to worry about the minus part in this case. Okay? So there's our relationship when solved for r. Why did I do that? Just because now I have a generic solution. And I can plug in the height. The height was given as 60. So let's go ahead and take the height and plug it in right here. Plug in a 60 right there. So this tells me when the height is 60, the radius is, and then we fill in the blank. Okay, it should turn out to be 5. 1,500 over 60 is 25, right? Because you cancel the zeros here. Makes it 150 over 6. That's 25, which is 5. My units are centimeters because the problem started with centimeters. Are we good on this one? Can we work on the next one with a partner? Work with the person next to you on the next one. It's tough. So there's a little bit of a tricky part here. Okay? You need to read this statement first. Here's what you're doing, folks. Listen, you're coming up with the equation based on this statement. You're going to have one equation, like we've been doing, like y equals k over x, or just a minute ago we had h equals k over r squared. Come up with an equation based on the variables here. Okay, and we'll call the force of gravity F. I didn't label that. Call the force of gravity capital F. Alright, so come up with your equation here. This is tricky. You might want to work with somebody. So to decide. If you think you have it, raise your hand. I'll go look.
Spherical bodies. So it's like
Talk with Chris. The two of you have somewhat or an idea as we're on track. Where you will visit. Chris is so far so good. You're going to add more.
I'm thinking M1 equals M2 over
Yeah, so guys, it's one equation. So far, Chris is on the best track. Chris, give me yours so far, Chris. Chris has it right so far, but he's missing stuff.
F equals K over R squared.
Chris says F equals K over R squared. That is definitely right so far, but he needs to incorporate something else about the problem. Okay, keep going. Yeah. What does it say? Is it that portion? It's not, because what are you doing to get K and F? These are multipliers, right? And it's virtually the voltage, so they're amplifying each other. So it's a multiplier problem. Dave's got it so far. Yep. Very close. You're missing a K, I'm just going for that K. And something's up about the M's.
Are you sure that's
You actually get
In the numerator if you want, or you can leave them there. Or you could put R squared, and then there's an extra A instead. You can follow what I'm saying? You can move it around and alternate. Nice, that's it.
You've done anything since
Yesterday, I knocked on the door and I was by myself with Mr. Pellegrino was right there.
What?
We call you Mark.
No.
No, Mark gave me that. I got it.
Is that a time?
Is
Is that a time? It is.
Either way, I
There are no numbers.
Good job, Arthur.
That's so easy. Alright, looks like everybody got it. Most people got it, not everybody right now. Alright, so let's take a look. It ends up becoming M1, M2 as a product in the numerator. Okay? And this is a difficult problem. So what we read, we say that it is the force of attraction between two spherical bodies is directly proportional to their masses. Now, some of you at first put M1 plus M2, but we have to have a product for something to be directly proportional always. That's why it's y equals kx, not y equals k plus x, right? So these are products, and then it's inversely proportional to the square of the distance r between their centers. So inversely to the distance r. It could also be written like this. Okay? With the k out front. Now, in physics, just so you know, it's not k that's written there actually. Instead of k, it's capital G. And it's the universal gravitational constant. And you write this as Fg. Okay? But that's a side note. Don't worry about that. But the idea is that you can come up with this. So let's take a look at the next problem. Remembering this, please. Remember. You can tell me what to do here. Oh, let's read it. The electric field produced by a charged particle varies. And you could start writing right away. You could use E for electric field if you would like. The electric field produced by a charged particle varies directly with the charge on the particle. And we'll call the charge on the particle, let's say Q. I'm giving you the variables that you use in physics. So the electric field E varies directly with the charge on the particle, we'll call that Q, lowercase q, and inversely as the square of the distance, we'll call that r, distance r, from the actual charge. So that first sentence, let's pause there and let's talk about that. The second part is our, situation. Let's look at the first sentence. What do you have? What do you have? From the first sentence, adapt this to what you had from the previous problem. How is it different? How is it the same? Chris. You sure? You started us off last problem, so you can start us off again. How is it the same, Chris?
Because you have the direct variation of the inverse.
Okay. So what do we start with?
KEQ.
Okay, so we're going to have K here for sure.
EQ.
All right, now it says the electric field varies directly. So we should start with electric field over here. Okay? So the electric field varies directly with the charge. So where should I put Q? If it's directly. Next to the K or in the numerator, right? Varies directly with the charge. The electric field varies directly with the charge. So far, so good. Varies directly, put it in the numerator. Varies inversely, put it in the... So what goes in the denominator? Not just R, R squared. And that's our equation. So directly, here's our key. Write this down. Direct variation, numerator. That's where the variable goes. Inversely related or indirectly related is in the denominator. Okay, so you're writing a little cheat sheet on the side. Write these notes down. All right, perfect. We're there. Turns out, by the way, in electrical engineering, the variable actually is K. It's called K with a little c, and it's called Coulomb's constant. Coulombs are amounts of energy named after a scientist with the last name of Coulomb. Okay? So it's K with a subscript of a c, and it's called Coulomb's constant. So we don't even need to change K for the real formula in electrical engineering. This is correct. Let's go ahead and look at our scenario now. The units are difficult to keep track of. Read the words to help you. So we're told on a planet galaxies away, the electric field felt at a distance of 13 meters. Where's that going to go? Distance. E is electric field, Q is charge, R. So 13 goes in for R. So this becomes right away now, we're also told the charge is 25. Where does that go? What's the charge, everybody? Q. Okay, it's what we defined it as. The charge was given as Q. And then we're told the electric field is 8 coulombs. So we solved for K in this problem. It looks difficult, but it's really not. You're just plugging in numbers. So you look at the values. It tells you distance of 13 meters. Whoops. Distance of 13 meters means that goes in for R. Charge is 25. That goes in for Q. Field is 8. That goes in for E. So you're literally just substituting in what you used in the beginning. You defined field as E right there in the beginning, up at the top. So you know right away that that's going to relate to the 8 there. You define charge as Q. That's going to be the 25 there. And you define distance as R. That's going to go in for the 13 over here. So use your values to help you as you go along the process. Solve for K. Give me K. What do you get as a decimal for K? Actually, it's a whole number, it turns out. I got a whole number value for K.
I got 54.08.
I got it as well.
You squared 13 to get 169.
Yes.
Multiplied that by 8. And then divided by 25.
54.08.
All right, I have wrong in my notes then. Thank you.
What did you get, by the way?
528. You know what I did wrong? I multiplied where I should have divided in one spot. I'll correct that. We all make mistakes. Ugh. So we got K. Now what do we want to do? We're not done with the problem yet. We've got K. What do we need to do?
Put it back into the
Plug it
equation.
into the original equation.
Yeah, so let's write the new specific equation. So E is now equal to 54.08 times Q over R squared. Figure out the next part yourself, please, from determine. From determine, please.
There we go.
You know why I did it backwards in my notes, folks? Take a look. I mixed up the units. That's why I did it. So the charge should have units of coulombs right here. That should read 25 coulombs. And the field should have read 8 newtons per coulomb. So I switched them up because I looked at the units one way. That's why the problem is written the wrong way. And that's the reason I switched it up when I got the different answer before. We're right still. We're still doing well. Okay, I just mixed up the units. So if you want to switch these 2 units to these units, that's what they should be. Okay, but if it didn't bother you, then don't worry about it right now. What do you get as a value for Q? What do you get as a value for Q? Hannah,
I'm not sure if I'm right, but I got
let's see.
40.3.
40.3?
Yeah.
Others agree?
I
Does anybody concur? So we should check it then, right? So did everybody do 18 times 11 squared? 11 squared is 121, right?
Yeah, and then
So 121 times 18,
is
enter, divided by 54.08.
Yeah.
What do you get?
I got 40.27,
So 40.3, okay?
I think you did the problem wrong, because we're not solving for Q, we're solving for E.
No, that's why I told you to switch the units, guys.
Oh.
I mixed up the units. Go back. Look, determine the charge. The charge is Q. Determine the charge. This is Q, remember? Q is the charge. The field is E. The distance is R. That's why, Dave, that's why I said to switch your units here in this part, okay? No, we're good. We're told earlier that the charge was given as 25, right? Remember the charge was 25? This should read 25 coulombs though, that's what I was saying. So correct your units here. Alright, correct your units there. The charge is 25 coulombs, that went in for Q, didn't it?
Yeah.
And now it says determine the charge. So we're finding Q. We're doing it right.
Oh,
Okay.
I thought 18 was wrong too. That's what I
You thought what was wrong too?
did. Since you switched the 25, I thought the 18 was wrong too.
No, the 18 is right. It says a field, right? A field is represented by E of 18 newtons per coulomb. That's going in right here for 18 at the bottom. Sorry, man.
Okay. I like got lost while we solved. Like we plugged Q 25 and 13, but then we.
So we were given a bunch of information, right? And we plugged it in here like you're saying. Then what did we do after that? We got a value for K. And we wrote the what equation? What do we call this? Specific equation? Remember this was the generic form? Remember earlier when you don't know K, we call it the general equation or just a relationship between the variables? Whereas this is specific to a certain scenario we were given. We were given the scenario that when the charge is 25 and the distance is 13 meters, the field produced is 8 newtons per coulomb. We found K as a result. We plugged that in for K in the original equation and wrote it this way. Then we were asked, determine the charge. So find Q when the field is 18 and the distance away is 11 meters. So we plug in those values and we found Q by multiplying by 121, that's what 11 squared is, and dividing by 54.08. All right? The units are what are mixed up in that problem there. That's why remember I said I had the different answer? I used the units backwards. So I'll switch them in the notes. Okay, if this confused you, I'll record tonight for sure. Just re-go through the problem for a little while. Okay, just listen to it and go through it on your own. The period of oscillations of a mass moving in simple harmonic motion. In physics, you know what that means? It just means a mass that is oscillating. Remember the spring you guys worked on last week? If you had let that mass go, the spring would have started doing this, right? Remember that spring that was really stretchy? It would have done this for a while. That's called oscillatory motion or oscillations. Simple harmonic motion or simple harmonic oscillations means that a mass is moving back and forth. So it would be going up and down on that spring without ever coming to rest if it did that forever. Like, you know when you raise those pendulum balls, Newton's cradle, and it hits the other one, it kicks the other one up, and those kind of go on forever? That's the idea of simple harmonic motion, but with one object. So we're told that the period of oscillations, okay, in simple harmonic motion, is proportional. So this is what I'm writing as I read. The period of oscillations is proportional to the square root of the mass m. Proportional to the square root of the mass m. So I write square root of mass m. It's still proportional because it's in the numerator. So we're good. But it's the square root this time. Who cares? It's the same problem. It's no different than the last one, just now we have the word square root. And it's inversely related to the square root of the spring stiffness K.
Use something else.
Yeah, we have to.
So what should we use? Well, no, we'll keep K here. What should we do to the other K? Let's change it. What do you want to call it?
L.
What? Not L, because L means length.
Oh, sorry.
Pick a random variable that we don't usually use.
V.
What? H. For your name, Hannah, is that what you're thinking?
Yeah.
That's fine. We haven't used H for much. I mean, height we've used it for, but we know it's not a height. It'd be a length, if anything, of a spring. Okay? So that's our equation. So in this case now, instead of solving for K, we have to solve for H to start, right? Solve for that constant of proportionality, or constant of variation. So we're told that the period of oscillations is 9.2. Where does that go in for? Take a look, folks, right here. Period is 9.2. What variable does that go in for? That goes in for P. The mass is 150. What does that go in for? And the spring stiffness, what was that defined as?
K.
It was defined as K. Go back up, right?
No, it's just confusing.
Spring stiffness K.
I forgot which one was.
So spring stiffness was defined as K, and the spring stiffness is 70. That'll go in for K. What is spring stiffness? The spring's rigidity. Remember in the lab? when one of the springs was weaker than the other, the mass pulled on that spring more than the other. That's the example we're looking at the tank. So we can plug in or we can solve for H. What would you like to do? You want to solve for H first in variables and then plug in numbers? Or you can plug in numbers. If you want to plug in numbers, go ahead and plug in numbers right now. I'm going to solve for H in variables. That's what H would be in variables. I multiply by radical K and I divide by radical M. Okay, again, multiply by radical K to get rid of a denominator. Multiply it up and divide by radical M. Let's go ahead and plug in now. Okay, again, you could have plugged in before. So period is 9.2, mass is 150, and spring is 70. So what does H become in this problem? I'll give you the value right now, just to save time. 6.28. Does that ring a bell? Where have you heard 6.28 before? What'd you get? 6.3?
I got 6.2.
Did you round?
Oh, I got 6.2.
Oh yeah. But think about the number 6.28. Where does that come about? Come on, number sense. It's a multiple of a certain number.
Pi?
Times.
Two.
Yeah, 2 pi. 2 pi is a general form that's in front of the period of oscillatory motion. 2 pi is the circumference of a circle with a radius of 1. You hear more about 2 pi in pre-calc. All right, so we've got H, right? We've got H. So let's rewrite this original equation at the top, but with 6.28 in for H. Okay, there's our equation now. And the problem says, what mass, right? What mass would produce oscillation? So we're looking for M with 15 seconds with a spring of 40. So 15-second oscillations with a spring of 40. Should I solve for M generically? 15 can go here, 40 can go here, 6.28 radical M. You have to multiply by radical 40, divide by 6.28, and then square both sides to get rid of the square root. Okay, watch the last part of the video tonight. This is the last piece. Okay, tonight regular homework. Back to regular homework. So look at the bottom of the notes. I'll put it on Moodle. What else do you need to do? Please. Surveys. Please, surveys. Tomorrow, I'm going to discuss the project in more detail about whether you're in groups of 2 or 3, so you can work on it this weekend. Okay? I'll be in the Commons on duty. Yeah. So come see me during duty. One-on-one duty. Natalie's also. Come see me during Commons duty, please.
During what?
Are you in 6th period Commons? When do you have a free?